Okay, so this third set of videos is going to be about graphing rational functions, and I'll probably do some more with that in the next set of videos, but let's just go ahead and kind of explore what we can find out right now. Okay? So the first thing I'm going to do is just talk about vertical asymptotes, and I've kind of mentioned this when we in the last set of videos when I talked about multiplicities, but let's go ahead and solidify that understanding, okay? So if I gave you the rational function y equals 1 over x minus 2, what that would mean is that we have a vertical asymptote at positive 2. Yep, at x equals 2. And because the lower power is in the denominator, I'm going to go ahead and write that. Vertical asymptote x equals 2. Sorry. And because the lower power is in the denominator, we know that we have a horizontal asymptote at y equals 0. And we also know that there is no x-intercept because the numerator never equals 0, so it never crosses the x-axis. Just from knowing functions, knowing that 1 over x looks like, and this is just a shift of it, I know it's down here and it's up there. Another way that we could do that is look at the y-intercept. So the y-intercept, if I plug in x equals 0, I get 1 over negative 2. So I know that that's at negative 1/2. And so that's a really big clue that the function is actually going to have to do this. Come from this horizontal asymptote. You have to lay out, so like you have to approach the horizontal asymptote, go through the y-intercept, and then go towards the vertical, right? Well, here's the thing. So this is necessarily going to pop up here because this has a multiplicity of 1. X minus 2 is only appears once. Um, now, another way I could check that is literally by just plugging in any number past 2 and seeing if it would be positive or negative, because it can't cross the x-axis, right? It has to approach either this vertical asymptote down here or this up here. So if it's positive, we have to be here, and if it's negative, then we have to be here, because these are my two guidelines, right? So if I plug in, say, 4. 4 minus 2 is 2. 1 divided by 2 is 1/2. It's a positive, right? So this has to do something like this. I don't really need like a specific value throughout here as so much as I need you to know that it's up here, okay? Uh, Same way if I had plugged in negative 1. So negative 1 minus 2 is negative 3. 1 over negative 3 is negative 1/3. And then, so I know that I would be down below the x-axis. All right? What I wanted to do, though, is really kind of explore what happened right here. This had to flip, whereas if I had asked you to graph this, whereas, I don't know how I just said that, whereas. Okay, so now in the denominator I have x minus 2, quantity squared. So I still have, let me draw those again. I still have a vertical asymptote at 2. And I still have a horizontal asymptote at y equals 0, because the power is higher in the denominator. And in fact, I still have a y-intercept that is, let's see, actually this time it's going to be positive because I'm squared. So if I plug in x equals 0, right, 0 minus 2 is negative 2, negative 2 squared is positive 4. When x equals 0, the y value is 1/4. So my y-intercept is actually right here, which means that this has to, if it has to cross here, right, then we have to come from here and go up, approach it from there. Now, if it was like this one, then it would flip, right? If it's up, then it's down. If it's down, then it's up. But because of this quadratic, so if I were to plug in 3, 3 minus 2 is 1, 1 squared is 1, 1 divided by 1 is 1. It's right here, which means this also comes from above. Okay? We'll explore more of that later, but in the next set of videos. But I really wanted to go ahead and address that right now so that you understand why I'm making that leap. If I know I'm down here, if it has a multiplicity of 1, then I have to pop up there, right? Now, What if it looked like this? What if I had a function that in the midst of all of it, it had an x minus 2 in the numerator and an x minus 2 quantity cubed in the denominator? Then one of those could simplify it with one of those, leave me with 2 in the denominator. That would be vertical asymptote with a multiplicity of 2, which means it would do this bounce type thing, meaning if it goes up, it comes from above as well. It does that repetitious behavior. Just like an x minus 2 quantity squared parabola would bounce at x equals 2. Okay? So we'll keep that in mind as we graph some of these functions, okay? So the first thing we're going to do is we're going to graph the function y equals 4x plus 4 over x squared minus 3x minus 4. So write that down. What I would do is I'm going to draw an x and a y. And I'm drawing, since you'll have to draw, so here we go. I'm going to go out 5 in each direction. I don't know what I need, but I figure that should be enough. No, that's terrible scale. Oh well. And let's talk about all the different things we want to know. Domain. Range. I'm including range because that's kind of an interesting thing when you talk about rational functions. X-intercept. Y-intercept. Vertical asymptote. Horizontal asymptote if there is one. I don't know if I want to conclude anything as far as in behavior. Oh, holes in the graph if there are any. Okay. So let's play around with this. I'm going to go ahead and factor the numerator, or factor the whole function actually. So I'm going to factor out a 4 and I'm left with x plus 1 in the numerator. I'm looking for the factors of negative 4 that add up to positive, or to negative 3. So I'm thinking negative 4 and positive 1. So let's start identifying what things are. X plus 1 is a common factor, right? Which automatically means, and it's the same amount of x plus 1s in the numerator and denominator, right? So that means that there is going to be a whole at x equals negative 1. Now I do want to know the location of that, so I'm going to plug in negative 1 into what's left over. 4 divided by negative 1 minus 4. So 4 over negative 5, that's negative 4/5. So negative 0.8. I'm going to go ahead and graph that at negative 1 and negative 0.8. Okay. All right. Now we're going to talk about what's left over. As far as my domain goes, I know that I have two issues in the denominator, positive 4 and negative 1, right? So positive 4 and negative 1, but negative 1 was shared. Either way, my domain is negative infinity to negative 1, negative 1 to 4, and 4 to infinity. So everything but negative 1 and 4. Which means 4 has to be something else, right? If it's not a hole in the graph, what is it? Well, if it's alone in the denominator, then it has to be a vertical asymptote. So I have a vertical asymptote at x equals 4. 1, 2, 3, 4. Okay. Then let's talk x-intercepts. So the numerator only equals 0 at negative 1, but we already know that to be a hole in the graph. So otherwise the numerator never equals 0 on its own, which means there is no, or there are none. There are no x-intercepts, which means it will not cross the x-axis. Y-intercept. So y-intercept is when x equals 0. So I'm going to plug in x equals 0 into the original, which means everything with an x goes away. 4 divided by negative 4 is negative 1. So I know that there's a y-intercept at 0, negative 1. Okay, so I'm going to plot that point. And, okay, let's talk about in-behavior model, the horizontal asymptote. So when you look at the powers in the numerator and the power in the denominator, the power in the numerator is 1, the power in the denominator is 2. If the higher power is in the denominator, that means the expression, like, on its own is going to get closer and closer and closer to 0 as x approaches the infinities, because it simplifies basically to 4 over x, and 4 divided by a billion is very small. So we have a horizontal asymptote at y equals 0. So just remember, higher power in denominator, horizontal asymptote at y equals 0. Okay. So I've got that. Okay. So what I think is pretty obvious at the, oh, well, we'll talk range in a minute. What I think is pretty obvious at this point is this function, right, might as well just be 4 over x minus 4, which is just a shift of 1 over x, right? It's a shift to the right 4 with a vertical stretch by a factor of 4, and then there just happens to be a hole in the graph, right? So I'm pretty clear. I know 1 over x looks like this. So anytime I do a transformation of 1 over x, right, it looks something like this. But it's also clear because I've got these two coordinate points down here that I have to either go to or go through. So in this case, I know that I have to be approaching the horizontal asymptote, right? I can't be up here and then come back down to get that because that would mean an x-intercept, but I don't have any x-intercepts, right? So if I'm down here and I have no x-intercepts, then I have to approach the vertical asymptote from below down here, right? So I have to approach it and I have to go down. I can't go up because that would mean an x-intercept, and I don't have any x-intercepts. So there, and then I know I need to approach the horizontal, so something like that. Don't make it unnatural and be like whoop and try to make it reach to it. And for the same reason, don't like draw it as if you're going straight to the vertical asymptote, because that does not convince me that you understand that you're going to be going towards the vertical asymptote. Now, I don't know what this graph looks like. It could have done something like this. It could have been a lot closer and done like that. Um, but as long as you have it going through these points, not through this one, but through that one, just going up to and then leaving from, and then approaching the vertical asymptote, then we're good. Right? So then here's where the multiplicity comes into play. Remember, the multiplicity of the vertical asymptote kind of tells me the behavior. So if this is a multiplicity of 1, and there's no other in the numerator, right? Then if this is down, then this has to be up. Okay, but I'm going to prove that. I'm going to plug in 5. Okay, I'm going to plug in 5 into what's left over. It doesn't really matter if I plugged in the original because the 6s will cancel each other out. But 5 minus 4 is 1. 4 divided by 1 is 4. It's positive, right? So I know that point, so I can plot it, but I don't need it. As long as I knew that I did something like this, then I would be fine. And so the fact of the matter is if this is down here, then this has to be up here because this vertical asymptote factor has an odd number of terms. An odd number of factors, I guess. It appears an odd number of times. Okay, so that means I approach it from above. And if I were to plug in any number past 4, then this would have a positive value. Obviously, because minus 4. Okay, so let's go back and talk about range. Range is low to high. So when I think about my range, I'm coming down here. This is approaching negative infinity, so I know I go from negative infinity all the way up until I reach this hole in the graph. So this hole in the graph occurs at the y value negative 4/5. That is the only time this curve will ever reach the y value negative 4/5, okay, because it's not wavering back and forth. So in fact, I know that I go from negative infinity up to negative 4/5, but I don't actually reach it because it's a hole in the graph. I pick back up at negative 4/5 and I go to the horizontal asymptote. I get closer and closer to 0, right? And I come from really close to 0, but I don't reach it. And so my range would be everything excluding negative 4/5 and 0. And that would be that graph. Okay, I'm going to stop the video and then start another one with the next problem.